And today we'll be seeing about some basic biasing circuits which were used conventionally, and then we will see what are the different specific circuits I have for BJT. Okay, I hope you can see this diagram here. So this is the biasing circuit which you have designed for a common emitter amplifier. So as you know, in a common emitter amplifier, so what is the input, what is the output in common emitter amplifier? What is the input and what is the output in common emitter amplifier?
Base inputs.
Base is the input and collector is the output. What will happen to emitter? What will happen to emitter?
Grounded.
Emitter is grounded. So is this diagram first logically representing a common amplifier? Yes, because you see I'm giving input to base, I'm taking output from collector, and my emitter is grounded. And since you know we are going to consider a common emitter amplifier, you are going to give AC input and you are going to take output across load RL. So as such, this when you are going to find these biasing circuit parameters, we will not be considering all these load. We will not be considering the AC input, and you can see two capacitance are there: CC at the input and CC at the output. So these capacitance coupling capacitance. Why the name coupling is because they need to couple the AC signal from the voltage source into the base. At the input side, this capacitor has to couple the AC signal from the input into the base. At the output side, this capacitor has to couple the AC signal from the output into your load. So for that purpose, you are using two coupling capacitors, CC at the input side and CC at the output side. Without coupling capacitors, you might not have efficient coupling of signal into the transistor, and you might not take out the signal effectively from the collector of your transistor. So these couplings capacitors are required when you are going to design the BJT for an amplifier purpose. But as such, what is important is we have to design these parameters: VCC, RB, and RC. See, definitely you need to have resistance in collector and emitter side because the resistance only can control the amount of current flowing through the circuit. So VCC is fixed. So we have to design RC and RB. So if we design RC and RB, we can fix the operating point, and the BJT will be working as a amplifier, and the Q point will be exactly in the center of your graph. Okay, so remember, this is a diagram for a complete common emitter amplifier. But if you consider only the biasing circuit, you will have only RB and RC. And among RB and RC, can anybody say which resistance will be larger and which resistance will be smaller? You have two resistance. Can somebody guess which one will be larger and which one will be smaller? Logically, can somebody say RB and RC, which one is larger or which one is smaller? Think, you have to think. Only when you think, you will get an answer. Think about the transistor current. You have two currents here: collector current and base current. Which current is smaller? Which current is larger?
Base current is smaller.
Base current is smaller. Can you say what is the order of base current? It will be in the order of how many? It will be in the order of what is the amount of current you can expect in a base? Milliamperes or microamperes or amperes?
Microamperes.
Microampere, and collector current will be in the order of milliamperes. So base current should be very, very less. So the base resistance should be very, very large. Collector current should be current is relatively higher. It is in milliamps. The collector resistance will be relatively smaller. So when you consider RB and RC, RB will always be higher than RC to restrict the current into your base, because base is very, very thin and it cannot withstand very high current. So for that only we are putting resistor at the base side to control the base current which is flowing into your base of your transistor. Okay, see, this AC input will have an AC current flowing into the base, and because of this DC input VCC, you will be having a DC current also flowing into the base. Okay, so this DC current will ensure the operating point of BJT, and this AC voltage will ensure the amplification input for BJT. Okay, so don't think that we are giving two inputs here, AC and DC. When you consider biasing circuit, you have to ignore all the AC components. You have to ignore the presence of VCC. You have to ignore the presence of CC. on both sides. Just take the DC components alone and design your circuit. That is going to be your biasing circuit. So biasing circuit, for this circuit, what you are seeing here, you have to design the value of RB and RC only. So VCC will be known. You will be given the value of VCC. You have to design the value of RB and RC. Okay. So to understand the basic biasing circuit, I'm not saying this is the effective circuit for biasing. This was the initial circuit used for biasing to fix my Q point or operating point in my BJT. Anybody is having doubts here? Anybody is having doubts in the basic biasing circuit? See, this load resistance, what you use is optional. You can directly take output from collector. If you want to specifically have a load resistance and measure V out, you can do that. Otherwise, you can whatever you take from collector is going to be again your output voltage only. And for biasing circuit, we will be considering the output characteristics of common emitter amplifier. Output characteristic means I'm going to draw the graph between output voltage and output current. Output current is collector. Output voltage is voltage across the collector emitter junction, VCE. So we'll be focusing only on the output characteristics curve for the biasing circuit. So output characteristics means in a common emitter amplifier, see what is happening at the output side. Output is collector. So collector current is IC along y-axis, and the voltage is going to be VCE, voltage between collector and emitter on the output side. So I'm going to draw the graph between VCE and IC.